Welcome back to ChemExam Explained, where the aim is chemistry clarity exam mastery. In this video, we will be looking at CAPE Chemistry Paper 2, Unit 1, Module 1, 2025. Let's go. Question 1, Part A. The sketch in Figure 1 below shows the first ionization energy of the 8 elements of period 3. So here you see your graph with the 8 elements across period 3. And our first question is to state 2 factors which influence the value of the first ionization energy. So here you are given 3. You can use any 2. 1, nuclear charge, 2, atomic radii, and 3, shielding or screening. Part 2. Explain how the ionization energy data provides evidence for the idea of subshells using appropriate elements from the sketch in Figure 2. So we'll be looking at these 2 anomalies here between magnesium and aluminum and phosphorus and sulfur. So in explaining the trend, we'll see that the general trend is an increase in the ionization energy, and that is consistent with an increase in the nuclear charge and a decrease in the atomic radii. The deviations include magnesium to aluminum. We'll discuss that one first. So the ionization of aluminum is lower than that of magnesium due to the aluminum outer electrons, and this is in the 3p subshell, which is higher in energy and less tightly bound than the magnesium 3s subshell. For phosphorus to sulfur, the ionization energy of sulfur is lower than that of phosphorus due to the electron-electron repulsion of the 4th electron being placed in the first 3p orbital. These anomalies provide evidence that electrons occupy different subshells, example 3s and 3p. Part B. Table 1 shows successive ionization energies for element D. We can see here that we are given the number of electrons removed, which is 12, and we have our ionization energy. But we are now supposed to convert the ionization energy in kilojoules per mole to log base 10 of the ionization energies. And so once you get your calculator, you'll put in log base 10 of 690 and you'll get 2.84. You'll do the same for the remainder of the ionization energies for the electrons removed. That would complete our table. And now we are to use the data in the table to plot a graph. And that graph is on page 7. And you're to plot the log base 10 of the ionization energies against the number of electrons removed. And of course, we were given the first plot. So let's get to our graph. Here you can see that we have on the x-axis the number of electrons removed. And we have 12 electrons removed. And on the y-axis, we have log base 10 of the ionization energies. You can see that the 2 electrons here with the highest ionization energy are the ones closest to the nucleus. And so these would be your 1s2 electrons. And this is your 1s orbital or subshell. Okay? The energy level, of course, is n equal 1. You'll see that the 8 electrons here now represent a subshell going farther away from the nucleus. And so we'll have 2s2 and 2p6. And these electrons are in the subshell further away from the nucleus, and they would now require a lower IE when these electrons are removed. And so these are the 8 electrons right here. These 2 electrons here would now be the electrons on the outer subshell, or the farthest from the nucleus. And now we have our 2 electrons that require the least amount of energy to remove them. And so from that, we can write the configuration to be 1s2, 2s2, 2p6, and 3s2. And so we can go back to our question. So part 3, we are to explain the shape of the graph. So the first 2 electrons are farthest from the nucleus, and these are your 3s2 electrons. and they belong to the same subshell or the same energy level. Okay, so once you remove those first two, these are the ones that require the least amount of energy to remove them. So now we're going to remove the third electrons, which will take us into the p subshell, which of course now will show a jump in the ionization energy, suggesting that we are moving closer to the nucleus, which is giving us evidence for shells. And so once we remove the third to the 10th electrons, we are now going to have another jump as we move to the subshell closest to the nucleus. And so we'll read for part 3. The first 2 electrons are farthest from the nucleus in the same energy level or shell. The third to 10th electrons are in the lower energy level, which is closer to the nucleus. The last 2 electrons are closest to the nucleus in a different energy level. Part 4. State the electronic configuration of element D based on the shape of the graph. So that was explained earlier, and we got 1s2, 2s2, 2p6, 3s2, and this element belongs to group 2 since it has 2 electrons on the outer shell. Part C. Substance S is a solid with a low melting point. A student is asked to determine the melting point of a sample of substance S by using the following apparatus and materials available in the school laboratory: a thermometer, capillary tubes sealed at one end, 500 ml beaker, Bunsen burner, tripod, gauze, and tap water. See Part 1. Outline fully the steps involved in the procedures that the students would follow in order to obtain the melting point of substance S. So the first thing we'll do is crush the solid sample and place it in the capillary tube. We'll then attach the capillary tube to a thermometer. We're then going to heat the capillary tube with the thermometer slowly in the water bath and observe the temperature when the solid just starts to melt. After that, we will record the melting point. See Part 2. Based on the melting point data obtained, the student concludes that sulfur is a covalent compound. Further analysis of substance S reveals that it is nonpolar. So the first thing we should note here, being that S is covalent and nonpolar, it means that it will have a low melting point. So low MP. And of course, it will be soluble in organic solvent, but not in water. So the question wants us to state whether substance S will dissolve in water or tetrachloromethane. And tetrachloromethane is an organic solvent. So substance S will not dissolve in water because it is nonpolar, but it will dissolve in the tetrachloromethane because a nonpolar solvent will dissolve a nonpolar solute. See Part 3. It was determined that substance S is a solid with a low melting point. Describe the type of forces of attraction that exist between the molecules of substance S. Well, the fact that it is nonpolar would mean that it has weak van der Waals forces due to the temporary induced dipole-dipole forces. Part D. Use the kinetic theory to explain each of the following. D Part 1. The change from a solid to a liquid state. Solid particles gain energy and start to vibrate faster, overcoming the forces of attraction, and the solid particles changes to liquid. D Part 2. The nature of the liquid state. The liquid particles are not closely packed and are held together by weak intermolecular forces. The particles in the liquid state have more kinetic energy than in the solid state, and the particles are able to move or slide past each other. D Part 3. The change from liquid to the gaseous state. The particles in the liquid state gain enough energy to overcome the forces of attraction and move far apart into the gaseous state. Part E. A gas syringe contains 18.2 cm³ of air at 55 degrees Celsius. A volatile liquid with a mass of 0.185 grams is injected into the syringe. The volume of gas in the syringe then becomes 54.5 cm³ at 55 degrees Celsius and 1.01 times 10 to the 5th Pascal. E Part 1. Calculate the molar mass of the liquid, given the molar gas constant to be equal to 8.314 joules per Kelvin per mole. So the first thing we'll do is we would write down the information given. And we have the mass to be 0.185. We have the volume, which is the initial volume, to be 18.2 cm cube. And we have the final volume to be 54.5 cm cube. We were given the temperature to be 55 degrees Celsius, which we must convert to Kelvin, and we know the pressure to be 1.01 times 10 to the fifth Pascal. So the first thing we'll do is to calculate the volume change, and that is the final volume minus the initial volume, and we get our volume change to be 36.3 cm cube, after which we convert that to meter cube using the conversion table. We then use our ideal gas equation to make mole the subject of the formula, and then plug in the information that we have for pressure, volume, the molar gas constant, and the temperature, and calculate the moles. After we know the moles, we then use moles equal mass over molar mass and make molar mass the subject of the formula, plugging in our mass and our moles that was calculated. And then we get our answer to be 137 grams per mole. It can be worked out another way using the ideal gas equation PV equal nRT. We are then going to make N be equal to mass over molar mass. And of course, we are now going to make molar mass the subject of the formula. So we'll multiply PV times the molar mass. That is equal to mass times RT. So molar mass is equal to mRT over PV. This is V, volume. And so now, if you do your calculation, your molar mass should be very close or equal to 137 grams per mole. So we can work it out more than one way using the ideal gas equation. E part 2 suggests which measurement used in the calculation of the molar mass is subject to the greatest error. And you can see that because we have our volatile liquid, as it is evaporating, the mass would change, giving us various mass change. And so that will give us the greatest error. This ends our question 3, module 3 for Unit 1, Paper 2, 2025. Thank you.